Hi everyone, this is Kalyan Kumar and welcome once again to Chemistry Universe. And in this video, we will be starting a new lesson from this one, and that is aryl halides. We've already finished alkyl halides, there were 15 parts to it, and you can check that out. And aryl halides, we're going to complete in 3 parts, it's a short one. And what we will be doing in this part, which I've titled as Introduction and ArSN2 mechanism, basically is going to tell you about the what is the basic difference between an alkyl halide and an aryl halide. And then, since we have been doing nucleophilic substitution in alkyl halides, we'll do something similar in aryl halides. We'll talk about the various reactions possible in aromatic compounds. And we'll focus on nucleophilic substitution on aromatic compounds. So first we'll do the nucleophilic substitution in aryl halides and a particular nucleophilic substitution in another aromatic system which is not an aryl halide. So this one is titled ArSN2 because aryl halides generally show 2 mechanisms by which they can substitute nucleophilically, and one is ArSN2, the second is benzene. So let's get on with the show and start part 1, introduction and ArSN2 mechanism. So the first thing is we need to understand what are aryl halides. Let's do the introduction first. Now aryl halides are compounds in which the halogen atom is directly attached to an aromatic ring. Meaning if I have this one, so do you think it's an aryl halide? What do you think? It's a yes, because directly attached to an aromatic system. What do you think about this? Is this an aryl halide? No, because it is attached to an alkyl carbon, not aromatic directly. So this is a no. What about this one? Well, this part is no, but this part is yes. So it is an aryl halide. What about this one? Well, it's not an aryl halide, so it's a no. What about this one? It is an aryl halide because you don't need benzene. You can even have any other aromatic ring. So here we have naphthalene. So this is the basic difference between aryl halide and alkyl halide. Now, before we proceed, we need to understand something about aryl halide specifically, and that is a dipole moment. Say, for example, I give you 2 compounds. I give you chlorocyclohexane and I give you chlorobenzene. Now, I want you to pause the video and think about which one will have a greater dipole moment and why. So, pause the video now. Well, as it happens, it is chlorocyclohexane. In cyclohexyl chloride, the dipole moment is only due to inductive effect. So basically, the dipole moment is in this direction. It goes up like this. So that is the dipole moment. Whereas in the case of chlorobenzene, besides the minus I effect, there is a plus M effect. So it's also giving electrons. It's due to both inductive and plus M effect. And the plus M effect, if you can understand, will go like this. And that is going against the inductive effect of pulling the electrons. So due to this, the inductive and the resonance effect in chlorobenzene act in opposite directions and thereby reducing its dipole moment. So now let's get a small idea about substitution reactions in aromatic compounds. Reactions of aromatic compounds are basically classified and we are looking at substitution reactions. Remember, we are not looking at all the reactions. Substitution reactions are basically 2 types, electrophilic and nucleophilic. And we are focusing on nucleophilic. So nucleophilic can happen in 2 types of substrates generally. One is aryl halide and the other is diazonium salts. And we'll talk about that in the 3rd part. Aryl halides can undergo nucleophilic substitution by 2 mechanisms. One is ArSN2, which is what we will do in this one. And then the next is benzene. So part 1 is ArSN2, part 2 is benzene, and then you have diazonium salts. So that is how we are going to deal with this. So diazonium salts will show ArSN1. Now, aryl halides undergo nucleophilic substitution with a great deal of difficulty. Now, we can clearly understand why this happens, because aryl halides have a pi electron cloud, so they're going to repel the nucleophile. On top of that, if you remember when we discussed alkyl halide, I told you aryl and vinyl halides do undergo substitution that easily because the leaving group, that is the halogen atom, has a partial double bond character. It's a stronger bond, not easy to leave. And getting a vinyl carbocation or an aryl carbocation is not easy because the carbon is sp2, and therefore it doesn't show any, as it is more electronegative. So plus is not going to be stable, and there are no resonance effects that help it make more stable. So generally, you'll find that aryl halides find it a lot difficult to undergo nucleophilic substitution. Firstly, the rich pi electron cloud of benzene repels the attack of any nucleophile. Secondly, there is a partial double bond character of the halide with the carbon of benzene. And thirdly, benzene carbocation is highly unstable as carbon is sp2 and is not easily formed. So how do we do that? Well, generally, if you want to really carry out nucleophilic substitution in aryl systems, we can do some of the following. What we can do is, we can introduce a strong electron withdrawing group at ortho or para position of the aryl halide, in which case it will undergo what we call as the ArSN2 mechanism, which we'll discuss in detail. The second thing you can do is you can use a strong nucleophile. Since the substrate is not very keen to undergo nucleophilic substitution, use a strong nucleophile. And thirdly, we can use vigorous conditions like high temperature and high pressure. So these will provide a conducive situation and environment for aryl halides to undergo nucleophilic substitution. So therefore, to carry out nucleophilic substitution in aryl halides, we need to either introduce a strong electron withdrawing group on the ortho or para position, use a very strong nucleophile, especially if the electron withdrawing groups are not present at ortho and para. And thirdly, use very high temperature and pressure. Now, in aryl halides, as I said, two mechanisms are possible for nucleophilic substitution. One, as I said, is ArSN2. The other, as I said, is benzene. So ArSN2 if aryl halide is activated by an electron withdrawing group, and benzene if the aryl halide is either unactivated or deactivated by electron releasing groups. Now here there is a very important thing that you need to understand. Very often when you do aromatic systems, you will hear the word activating group. You'll hear the word deactivating group. And if somebody were to ask you, well, is this group activating or deactivating? The answer is you can't say anything. I mean, there's no answer. The question is wrong. The question should be, is it activating towards nucleophilic substitution or is it activating towards electrophilic substitution? And they will have opposite answers. So here in this, since we're talking about nucleophilic substitution, remember we want the benzene ring to be less electron rich to allow the nucleophile to come in. And that is only possible when you have a withdrawing group, a strong withdrawing group, especially ortho or para to the leaving group. And why it is so, you'll understand when I show you the mechanism. But if the ring has a releasing group, that is a deactivating group for nucleophilic substitution, or there is no other group besides the halogen, then it undergoes benzene mechanism. So let's start with the first one, ArSN2. So we're looking at ArSN2 mechanism, and we also call it addition elimination mechanism because first something adds and then that thing leaves. And so like this, you have the para-nitrochlorobenzene. I use a strong nucleophile like OH-, vigorous condition 150 degrees Celsius and 10 atmosphere, and the Cl gets replaced by OH, nucleophilic substitution. And let's see how this happens. Mechanism of ArSN2. And as you can see, when I say ArSN2, I'm talking about aromatic substitution, nucleophilic, pi-molecular. So step 1, you have paranitrochlorobenzene, and you have the nucleophile. The nucleophile attacks the carbon with the Cl, and the pi bond breaks towards this carbon, and you get a carbonyl. And as you can see, the carbonyl is conjugated with this double bond and will undergo resonance. You get the minus on para, and then this again goes to ortho. And in fact, when it comes to para, remember the nitrogen has an N double bond O group, and there is a ring with a negative charge here. So it will undergo an additional resonance, giving you a fourth structure, which I'm not showing you right now, but it gives you a fourth structure, extremely stable, perhaps more stable than the ones in which the minus comes on carbon. And the resultant thing is you will get something like this. This is why we need a strong withdrawing group at ortho and para, because the negative comes at ortho, para, ortho, which is why we need a strong withdrawing group at these positions. And this is the hybrid. Now, this is called the Mesenheimer complex. Now, in the second step, the minus comes back and the leaving group Cl leaves, resulting in the product. Now, I want you to think about and find out, after having seen this mechanism, the two steps. Which minus comes? Pi bond leaves. Pi bond comes, Cl leaves. I want you to think about how would you experimentally find out which is the RDS. Now we can say, okay, this step is RDS because this is happening. This should be slow step because this is difficult to form. But remember, all of those logic come only after knowing which is the RDS. Right now, we don't know what the RDS is. So if you were to be asked to do an experiment to find out what is the RDS, how would you do that? I want you to pause the video and think about it. Well, the slow step can be found out by changing the nucleophile, changing the leaving group, and adding the electron withdrawing group at ortho and para position. Now what happens is, if the first step were RDS, changing the nucleophile will definitely have an impact on the rate of the reaction. And if the first step is the RDS, then leaving group's nature is not going to affect because the leaving group is not leaving in the RDS. If this were the RDS, the presence of NO2 at para was really going to help speed up the reaction. Whereas if step 2 were RDS, then what will happen is that the leaving group ability becomes important. So these are the ways by which one can practically find out which is the RDS. And as we can see, this is the RDS and this is the fast step. Now, why would that be? The first step is the RDS, slow step. The nucleophile attacks the carbon having the halogen because only that carbon has a delta positive charge due to the halogen and a good leaving group. Now, the reaction could have been a one-step process where the nucleophile attacks and the leaving group leaves, just like SN2. So you may wonder, why doesn't the nucleophile come and the leaving group go? Why does it that the pi bond breaks first? Then the pi bond comes and the Cl minus leaves. We did have that in SN2. Nucleophile attack, leaving group go. Well, there are several reasons. Reason number one, the nucleophile has to attack from the back side. It can't attack from the front side. Because remember, in the transit, it has to attack the sigma star of the leaving group bond. Or you can say that in the transient state, you have both the nucleophile and the leaving group both carrying similar charges and they don't want to be in the same side. So they have to go from the opposite side. It's almost impossible for the nucleophile to swim through the electron cloud of benzene and attack the carbon from the back. The second reason, as I said, partial double bond character. It's not going to be easy for the leaving group to leave. Now you may wonder, After all, the leaving group is leaving in the second step. So what was the harm in leaving the first step? In the first step, there was a partial double bond character. In the second step, it's not. And I'll just show you how. Now, this does not happen because of three reasons. If the leaving group tries to leave in the same step in which the nucleophile attacks, the transition state would show both the nucleophile and the leaving group carrying partial negative charge. Since the nucleophile approaches the electrophilic carbon from the side in which the leaving group is attached, in the transition state, both the leaving group and the nucleophile would carry the same type of charge and attached to the carbon on the same side as each other. Now, this repulsion between similar charge species would destabilize the transition state so much that it doesn't simply happen. Therefore, for the leaving group to leave in the same step when the nucleophile attacks, the nucleophile has to attack from the backside of the leaving group, like SN2. Now, the nucleophile cannot come from the backside of the leaving group because it will then have to move through the pi electron cloud of the benzene ring. The repulsion between the nucleophile and the pi electron cloud would prevent the nucleophile from attacking from the rear of the electrophilic carbon. Moreover, the bond between the leaving group and the phenyl group is partially double bond due to the lone pair double bond resonance. Therefore, the bond is not easy to break. In step 2 of SNAR, the mechanism, the leaving group is able to leave because the bond holding it with the phenyl ring is just a single bond, and the plus I effect of the carbon ion helps push the leaving group out. So if I were to just take you back, just let me show you the previous slide. Now, if you look at this step 2, you will notice this Cl's lone pair is not conjugated with any double bond. So there is simply no resonance happening. It's purely single. Moreover, the plus I effect of group would make this Cl leave. Now let's look at the free energy profile. Now in the free energy profile, remember there are two steps. So you have the first step and the second step. The first step is the RDS, which is why it has a bigger activation energy. And since the first step is RDS, the rate law would be rate equals K into substrate into nucleophile. And the rate of SN2 would be directly related to the stability of the carbon ion formed, which is why you need strong withdrawing groups at orthopara. Directly proportional to the electron withdrawing groups. Inverse to the electron donating groups. In fact, electron donating groups don't even show ArSN2. And nucleophilicity of the nucleophile. Now I'm going to contradict this shortly. Even though the nucleophilicity is important, because after all it is the nucleophile which is attacking in the RDS. But sometimes even a weak nucleophile can do the job. Of course, not as fast as a strong nucleophile can. And the reason the weak one can do it is because the negative charge is being stabilized by electron withdrawing groups at ortho and para. So even a weak nucleophile to some extent can do the job. So even a weak nucleophile can carry out ArSN2, though a strong one will work faster. And as you can see, the leaving group ability will not be seen as it leaves in the fast step. And if at all you have multiple leaving groups and you want to know which is going to be faster for ArSN2, look for the one in which the carbon becomes more and more delta positive because of the leaving group. The more delta positive it is, the more are the chances, the more easy it is for the nucleophile to attack that particular alpha carbon. So, greater the positive charge on the alpha carbon, faster will be the rate. Let's look at some examples. You have fluoro, you have bromo, you have iodo, and you have chloro. 1, 2, 3, 4. I want you to pause the video now. Write the decreasing order of reactivity and then play the video back. The order will be 1, 4, 2, 3 because this is more electronegative, makes the carbon more delta plus, then the 4, then the 2, and then the 3. Okay. Now I want you to check out this one. These 3. Which one do you think? Obviously, electron withdrawing group is only in 1, and 2 in fact is a releasing group, so it will be at the end. So it will be 1, 3, 2. What do you think will happen with this? Pause the video, make the order on your own, then play it back. Obviously, ortho and para would be better. So meta would be the least. Among ortho and para, ortho would be slightly higher because of a greater minus I effect. Now, as the number of electron withdrawing groups increase, you'll also notice that the rigorousness of the condition becomes less stringent. Say, for example, if you have one nitro at ortho, and even if you use a weak nucleophile like ETOH, you can still carry out the reaction, but at 300 degree and 10 atmosphere, and you get OET, the ether. But if the same thing had two NO2s and the same nucleophile, the condition becomes exactly half. That, of course, is not a necessity, but in this case, it does. And you get this. And when it comes to three of them, well, the condition even becomes less stringent, 75 and 2, and you get this. And on top of this, if you had a strong nucleophile, well, it almost occurs at room temperature. And then at the end, I just want you to understand that if this were ever reacted with a phenoxide ion, the general tendency would be to use O minus to attack this carbon and replace this Cl. But instead what happens is the O minus comes here, the pi bond goes here, this becomes minus, this attacks the Cl and the pi bond goes here. So what would happen is the one with the chlorine would look like this. Chlorine, negative, double, double, and there's an NO2 here. And this would be attached to the ortho carbon of the phenoxide ion. So, so it will have a H here, it will have a double bond O here, double and double. In the next step, what happens is the minus comes back as usual, Cl leaves. The Cl picks up the H and this makes this also aromatic. So eventually both these rings are going to become aromatic. So the problem, the product you have is an ortho product and a para product, because the negative come also in ortho and para. Now here comes a problem. In some reactions you will find the O attacking in phenoxide. In some of them you will have the C attacking. And I'll give you a detail of this when does O attack and C attack in phenols. But right now what you can understand is that, you know, O minus is a hard base, highly electronegative element, hard base. C minus is a soft base. Now here the electrophile, if you remember, is chlorobenzene, the carbon of the chlorobenzene. And that is not that highly delta positive, because Cl also has a releasing effect. Therefore, it's a soft acid. So according to the hard acid, hard base, soft acid, soft base theory, a hard base attacks a hard acid and a soft base attacks a soft acid. So C minus, this particular C minus has a greater tendency to attack this soft acid carbon delta plus. So that is how it is going to happen. And the last example for this video, what about this one? Rather, the second last example. Obviously, you can't do anything with the ortho. Not only is it hindered, it doesn't have an H also. And in the end, you have to remove the H. So the only way it can attack is para. Try this. This is called a trichlorotrazine. And if I were to attack with ammonia, I want you to pause the video now. Make the product. Play it back again. Obviously, the Cls will go and replace by NH2. And this is called melamine. The compound using which you make unbreakable crockery. And that finishes part 1, a short one on introduction and ArSN2 mechanism. So that's the end of this video. In the next one, we will be talking about the benzyne mechanism, the second mechanism, which happens only when the aromatic ring is unactivated or deactivated by a releasing group towards nucleophilic substitution. And in that, we will talk about various types of reactions, the mechanism, the RDS, and everything that we did in this similar to that. And that video also is going to be pretty short. This entire lesson is going to be pretty short. At the end of that second part, we will be doing benzene diazonium salts, where we do ArSN1. Though benzene diazonium salts are not a part of aryl halides, but since we are doing nucleophilic substitution in aryl halides, we might as well do that part. With that said, this is Kalyan Kumar signing off. Have a wonderful day and thank you for watching this.